And now we're going to transition to the last talk of the morning talk of today, and it's gonna be a wild safari. Ian is gonna tell us about all sorts of machine learning platforms that we have, and maybe we are gonna see that there are some overlapping opportunities and opportunities for us to collaborate and just converge into a single one.
Greetings, my name is Ian Hellström, and I shall be your guide on this safari through the wilderness of machine learning platforms. I have spent the last decade tinkering with data and machine learning as an engineer at Spotify, Bosch, and more recently, D2iQ, where I am the product manager of Captain, D2iQ's end-to-end machine learning platform powered by Kubeflow. Cloud-native machine learning platforms are a recent phenomenon. After the initial waves of platforms spotted at tech companies, an entire ecosystem of commercial and open source platforms has emerged. We shall peek at the early incarnations as well as off-the-shelf platforms. Based on these, we can observe a few emerging trends. Fasten your seatbelts, keep your hands inside your chairs, and let's drive through the landscape of end-to-end machine learning platforms. Although machine learning and artificial intelligence have been around for decades, end-to-end platforms for the big data era have not. That era started with Hadoop in 2004. Spark joined the fray a decade later, and in the same year Google open sourced Kubernetes, kicking off the cloud-native age. Torch and Theano were responsible for early progress in deep learning, although nowadays most of it's done with TensorFlow or PyTorch. These were released in 2015 and 16 respectively. Cloud-native end-to-end platforms with support for deep learning have not popped up until fairly recently. The oldest species of such a modern machine learning platform is merely 5 years old. Let's take a closer look at some of the machine learning platforms of the tech companies. In 2016, Facebook was the first tech company to publish details of their platform FB Learner. The work on FB Learner started in late 2014 with 4 objectives. 1, to implement each algorithm only once. 2, to allow training pipelines to be parallelized. 3, to automate each step of a pipeline. And 4, to enable experiment search and at-will rerunning of experiment variants. FB Learner Flow dealt with exactly that, training and evaluation of machine learning models. It consisted of 3 components: an execution environment for distributed workflows that relied on Python decorators, a UI for experimentation management, and predefined pipelines. Initially, FB Learner was built on top of Lua Torch and Caffe 2. PyTorch was originally developed at Facebook to accommodate the modern Python-based stack. Nowadays, there's also support for PyTorch Lightning, Catalyst, and FastAI. And of course, hyperparameter tuning is available out of the box too. Details of Facebook's feature store and inference infrastructure shown here emerged in 2018, along with details on custom hardware. The next company to announce details of the machine learning platform was Twitter. Work on DeepBird started with several acquisitions that led to the creation of the Cortex team in the summer of 2015. Its goals were unifying and improving usage of AI for all engineers, streamlining difficult ML processes, and freeing engineers to focus on modeling, experimentation, and user experience. Their platform is also based on Python, but like Facebook's, it ran on Lua Torch until mid-2017. TensorFlow has since become the framework within Twitter. Interesting to note is that TensorFlow estimators are able to address most of Twitter's use cases. Shown here are the steps involved in the 3 supported modes: training, evaluation, and serving. The function names take after the TensorFlow estimator API. Although Twitter's orchestration engine is Aurora, they chose Airflow for machine learning and built a dedicated Aurora operator. Their platform includes hyperparameter tuning operators too. In 2019, Twitter also shared details of the feature store that nowadays powers DeepBird. Details on Google's TFX, or TensorFlow Extended, were published in 2017, although its predecessor, Sybil, had existed since 2007. Sybil enabled massive machine learning, but it had no support for deep learning. In 2015, as we've seen, Google open sourced TensorFlow, but Sybil lacked the flexibility to integrate TensorFlow. Several of Sybil's key components later ended up in TFX. TFX was built to reduce the time to productionize machine learning models from months to weeks, as their engineers and researchers struggled with deployments. Each step in a TFX pipeline, indicated here by a box, produces artifacts or outputs that can be used by subsequent steps as inputs. These artifacts are stored in a central machine learning metadata store. Artifacts are indicated by the dark boxes. To minimize training serving skew, TensorFlow transform, shown as one of the orange boxes, freezes values in the TensorFlow computation graph, so that the same values found during training are used when serving. What may be several operations in the DAG when training will be a single fixed value at serving time. Around 2015, Uber's ML engineers noticed the detrimental consequences of scaling ML due to the oft-heard phrase, "but it works on my machine." Uber had built custom one-off systems that integrated with ML models, which was not very scalable in a large engineering organization. That's why they built Michelangelo. It relies on Uber's data lake, and it supports both offline and online predictions. For offline predictions, containerized Spark jobs generate batch predictions, whereas for online deployments, the model is served in a prediction service cluster, which typically consists of hundreds of machines behind a load balancer. Michelangelo can deploy multiple models in the same serving container, which allows for safe transitions from old to new model versions and side-by-side A/B testing of models. For feature engineering and storage, Uber built Palette. It consists of an offline feature store in Hive and an online one built on top of Cassandra. It was the first feature store to be described in detail, and it has inspired several since. The next company to talk about their ML platform was Airbnb. Airbnb established their own ML infrastructure team around 2016-17 for similar reasons. Big Head is the culmination of their efforts. Feature management is handled by the in-house tool Zipline. It is a company-wide crowdsourced feature repository that is powered by Spark. It includes automatic monitoring of data quality and allows point-in-time backfills of data, among others. Redspot is a hosted, containerized, multi-tenant Jupyter Notebook service. The Big Head library, not shown here, is for data transformations and pipeline abstractions, and it holds wrappers for common model frameworks. It preserves metadata through transformations, so is used to track lineage too. The Big Head service is responsible for model lifecycle management. It keeps track of all versions of models across development and production. It allows experiments to be set up and monitored too. The Deep Thought service is a REST API for online predictions. As can be expected, Airflow, their own workflow orchestration engine, runs all DAGs, although tasks are specified declaratively in ML Automator on the bottom left. These are then translated into Airflow DAGs. The entire Big Head platform runs on Kubernetes. LinkedIn's ProML stands for Productive Machine Learning. Its goal was simple and by now familiar: to double the effectiveness of machine learning engineers while simultaneously opening the tools to engineers across the LinkedIn stack. The LinkedIn engineers made it clear they wanted to use and improve the best components of their stack, as they had no intention of rewriting any. Systems running models in real time had to be able to upgrade independently without breaking downstream services. And the platform had to be flexible enough to allow state-of-the-art algorithms and frameworks to be added later on. ProML integrates with Jupyter Notebooks for exploratory work, such as data exploration and feature selection. For offline training, which is used for the bulk of LinkedIn's products, they rely heavily on Hadoop in conjunction with Spark and Azkaban, a batch workflow job scheduler that was developed at LinkedIn itself. Later, they relied on PhotoML, a replacement for Spark's MLlib. TensorFlow on Yarn is used for deep learning too. Like Twitter, LinkedIn used Spark with Scala for data processing. Health assurance, shown on the side, ensures that online and offline features are statistically similar and that the model behavior is in line with expected behavior. This includes anomaly detection. Frame is LinkedIn's feature store, which includes both online and offline features. Netflix faced exactly the same issues as the companies we've seen so far. To make their data scientists more productive, they focused on notebooks as the core component. Interact is a React-based UI for Jupyter notebooks, shown as the entry point for users at Netflix in the top left corner of the image. Papermill is an Interact library used to parameterize and execute notebooks. These parameterized notebooks can then be scheduled with Meson, Netflix's general-purpose workflow orchestration and scheduling framework. All workloads are containerized, and whenever a notebook server is launched, a container with sensible defaults for resources is provisioned. Titus, shown in the image, is a container management platform built internally at Netflix. In the top right, you'll see Commuter, a lightweight service for viewing and sharing notebooks. It is read-only. Model lifecycle management, not shown here, is managed by Runway, an internally developed solution. The platform also includes Fact, a facts and feature store that allows time travel on features. It's why the feature generator is called DeLorean, as a nod to Back to the Future. DeLorean relies on Hive tables backed by S3 snapshots of logged facts and a JSON-based feature model to encode these features. It bridges the gap between data warehousing and machine learning use cases. Feature encoders can be shared to avoid training serving skew. Metaflow has since been open sourced, although it is still intimately tied to AWS infrastructure, and it does not cover all of Netflix's internal platform. Before Krylov, eBay's data scientists needed weeks, sometimes even months, to become productive. They often had to procure and manage infrastructure, move data to the machines, and install frameworks themselves. While Krylov does not show anything we have not encountered on our Safari yet, it does highlight the common components that have emerged over the years. Next, Spotify. Spotify initially had teams doing machine learning on a one-off basis, each with bespoke infrastructure that needed to be maintained by individual teams or squads in Spotify speak. Since their entire infrastructure is in GCP, and after several iterations, they went with TFX components on top of Kubeflow pipelines, using Python for both machine learning and feature engineering. As you can see, the ML platform also supports XGBoost and scikit-learn, as Kubeflow pipelines is entirely containerized. Each step in a pipeline is a separate container. Luigi is used for dependency management, as is the standard tool for that at Spotify since its inception during the early days of Hadoop. All tools integrate with the now open source central management platform called Backstage. The last tech company on our Safari is Lyft. In line with their desire to style eyes with Ys, they developed Flight. Flight is a workflow platform built on top of Kubernetes. It focuses on platform abstractions for complex workloads and dependency management. As such, it's not a machine learning platform per se, although it is used internally to run machine learning at exceptional scale. Not unlike Metaflow, it comes with a Python SDK for authoring workflows and versioning both code and artifacts. Flight caches output so that both time and money can be saved if a workflow with the same parameters has already completed successfully and is scheduled to run again. All entities in Flight are immutable, so it's possible to track data lineage, reproduce experiments, and roll back deployments. Flight has since been open sourced. And that, ladies and gentlemen, concludes the first section of our Safari. What have we seen so far? A few things are obvious. Open source is a core component of all these platforms. Companies heavily rely on it, but they also contribute extensively. Containers are used to handle code and dependencies consistently and in an isolation of every other workload. It's also obvious that Python has emerged as the lingua franca of machine learning. Note that there are a few companies who rely on R or even Scala for machine learning, but they are in the minority. That said, TensorFlow is the leading framework for deep learning, with PyTorch gaining ground. XGBoost also seems to run in quite a few companies, as well as specialized libraries for NLP and computer vision. Spark is sometimes used for ML, but mostly for distributed processing of data. Whether that be in Scala or Python often reflects history. Twitter and Spotify both have rich traditions in data processing in Scala, with Scalding and CO. Other companies prefer to have the same programming language for data engineering and data science. Kubernetes is also becoming common across companies who have built their own platforms from scratch in the last 2 or 3 years. It has already beaten the competition in container orchestration, so it's no surprise it's gaining ground as the de facto infrastructure for machine learning too, as most companies have already settled on containers anyway. In terms of ML-specific components, there are a few trends visible. AutoML, specifically hyperparameter tuning, is becoming a standard step in pipelines. This allows the best hyperparameters to be found without guessing or manual tweaking. Notebooks are here to stay too. Companies such as Netflix have even centered their environment around it. Workflow automation with directed acyclic graphs have become standard too. There does not yet appear to be a standard around tooling, although Airflow has overtaken Luigi in data engineering tasks. For machine learning though, both are used, but there are also Kubeflow pipelines and several newer options: Flight, Dagster, Prefect, and Kedro. No clear favorite has yet emerged. Integrated data quality monitoring and drift detection are essential to production machine learning platforms. Many custom feature stores come with anomaly detection and monitoring of data distributions over time. And finally, most companies have integrated their machine learning inference infrastructure with their experimentation platforms to ensure they can A/B test model tweaks before rolling out major changes to millions of users. The logos shown on the right represent the platforms I have looked at in detail. It is by no means an exhaustive list of companies who have published details of their machine learning platforms, but it is to my knowledge the largest gathering of such information to establish trends across said companies. You can find links to these and more on the page indicated on the bottom right. That's of course all nice, but what about commercial platforms? Most companies do not have the resources or desire to build a platform from scratch, and in many instances it's not even sensible to do so. I won't go in as much detail here because there are even more platforms out there than we've zipped past so far, but let me share some high-level observations. In the chart, you can see the 65 plus platforms I looked at in detail. This list is again not exhaustive, but it does cover the main suspects. The colors go from dark blue to bright yellow, and they indicate the visibility of the product in the marketplace, which is based on social media followers on a logarithmic scale. Anyway, what you can see is that there are quite a few end-to-end platforms. So let's dive into data a bit more. Here we see the relative size of each category, the type of platform, the infrastructure shown in the middle, and whether these offerings are open source or proprietary. The majority of platforms are proprietary, which is perhaps not surprising. There's a lot more than meets the eye when building a full-scale machine learning platform, as we have already seen. And that means there's money to be made by providing the 95% of glue that holds together production machine learning systems. What is clear is that Kubernetes has become the de facto standard for modern machine learning infrastructure. Kubeflow, a machine learning toolkit for Kubernetes, is inside quite a few offerings, particularly its pipelines component. Kubeflow pipelines is even found in some cloud vendors' products such as SageMaker and AI Platform. Kubeflow pipelines has also been spotted at organizations such as CERN, Snap, and Zeals, and of course Spotify that we saw earlier. While several traditional platforms were built before the advent of the cloud-native tool suite, and they often rely on servers with VMs for training, they typically use Kubernetes for serving. The majority of platforms out there require users to code with common machine learning libraries and deep learning frameworks, which of course means users can benefit from the latest in the open source community. A few go down the no-code path, which to some extent democratizes machine learning by opening the field up to non-technical users, but of course it also increases vendor lock-in. The no-code or low-code platforms are generally appropriate for traditional tabular machine learning use cases. The on-premise market is significant for machine learning, as many enterprises still have on-premise data centers. However, it is obvious that few platforms are built for air-gapped or fully offline environments. Quite a bit of additional effort is needed to be able to install and operate a machine learning platform without access to the internet. Customers in government, defense, intelligence, banking, insurance, manufacturing, and so on still rely mostly on on-premise or air-gapped clusters with no intention to move their data and workloads to public clouds. That is not to say that there is not a steady drop in on-premise hardware expenditure due to the migration to public clouds. There obviously is. I should also note that platforms listed here as on-premise can also run in public clouds and in some limited cases in hybrid or multi-cloud environments, such as for instance D2iQ's Captain. Finally, feature stores are still fairly rare in commercial tools. You tend to only see them in end-to-end platforms for obvious reasons. Apart from improving feature discoverability and collaboration, feature stores can minimize or even eliminate training serving skew, which is a particular concern in end-to-end platforms. In development platforms, serving is not a concern, and likewise in deployment platforms, managing features for training is not important. Google announced in September they would add a managed feature store to GCP's AI platform by the end of last year, but that has not yet happened. With that, let's revisit the trends we glanced at earlier. Essentially, the trends are the same as with the tech companies' DIY platforms. For instance, many proprietary platforms rely on lots of open source technologies, and a fair amount of vendors contribute back to the community. Where we see a difference is in platform features unique to machine learning. While all are covered by some platforms, few platforms offer the complete package as of today. Hyperparameter tuning, for example, is available in several platforms, but it is not yet included across the board. Some commercial platforms offer sophisticated automatic feature engineering capabilities, but they are in the minority. Feature stores are not prevalent at all. Most of the available feature stores, shown on the right, are not that mature yet. Beyond the novelty, my personal feeling is that feature stores have not yet become mainstream, simply because their benefits only become apparent when scaling machine learning across many teams in an organization, where reuse of millions of complex features can speed up model development considerably. This requires a solid and established data engineering practice within the company, as well as a certain amount of discipline with regard to documentation, maintenance, and of course vetting of features, without which a feature store can easily end up being a data dumpster. Pipelines and workflow automation are fairly standard across end-to-end platforms, especially those based on Kubeflow, but they are not yet a given everywhere. Data quality monitoring is available in some platforms, but it's definitely not as widespread as one would hope and, dare I say, expect. As feature stores are integrated into increasingly more platforms, drift monitoring is set to become more ubiquitous too. Lastly, we see a lot less direct integration capabilities with experimentation platforms, which is more or less expected. While A/B tests provide crucial product feedback to consumer apps, they are less critical in enterprise environments. Canary deployments and pre-production shadowing are still not that common, although a few platforms offer it out of the box. Shadowing is sometimes referred to as champion-challenger model deployments, in case you're more familiar with that term. These gaps will be addressed continuously as cloud-native end-to-end machine learning platforms become commodity infrastructure in enterprises across the globe. And with that, we have come to the end of our safari of machine learning platforms. I hope you enjoyed it and grabbed some souvenirs along the way. Thank you.
Thank you, Ian, for such a thorough safari. It's been quite a journey. I'm sure everyone enjoyed it as much as I did. It's been really fascinating. So much information in so little time. Oof. And we are also criminally out of time, so I think I'm gonna just try to go with the question myself. So the question would be, so you mentioned that there are so many open source solutions for ML ops in the wild, and why do you think we need them? Like, is there? I understand that with commercial offerings, they try to differentiate themselves just so that they can, sell their services and products. but why do we have so many open source technologies?
I think there's several reasons for them. I think the main one is history. So a lot of these technologies came out of the various tech companies, and they all developed their own tooling independently of the others. You can basically see that with PyTorch and TensorFlow. They came out of Facebook and Google respectively, and they have essentially become the standard for model development. In terms of ML ops, I think the field is still fairly new, and some of it has grown out of data engineering. So for instance, for pipelines and dependency management and workflow orchestration, you will see the Luigis and the Airflows out there, which have come essentially from data engineering. Then there's sort of the cloud native generation 2 of that with Flight and Daxter and Prefect. And then you have a couple of others like Kedro, which is more an interactive version of that. You kind of see that they come out of other fields and they try applying their methodology to machine learning. And I think you will see that a lot, that DevOps is being applied to machine learning and people call it ML ops. I think there's a couple of major differences between DevOps and ML ops that really highlight that it's a different field, it's a different level of complexity. So one thing that I always look at is how we look at CI/CD. In traditional software development, you essentially deploy the final artifact. So if that's a back-end microservice, if that's a front end or something like that, it's deployed and that's the end of it. You basically test it and it's deployed. You just have one artifact. In machine learning, and in a way it's similar with data engineering, you deploy the factory, not the final product. So you want to have the whole pipeline that goes from data ingestion, transformation, model training, tuning, and the decision that automates whether you deploy and how you deploy. So for instance, if it's a shadow, a canary, just a hot swap of a model, you want to deploy that because when you retrain the model, you need to have the whole data pipeline that feeds it run again or from a new point in time, or as just an addition to what you've trained on before. You don't want to rerun the training over 5 years of historical data again. You do that from a point in time. So essentially, you need the whole pipeline that builds that. In case you change something in the data, in the semantics, in the transformation, that has to be changed too before deployment. So you don't deploy the final artifact, you deploy the whole pipeline, which I call deploying the factory, not the final product. And I think that's where you will see that a lot of the DevOps tooling is being applied, and there's a lot of DevOps tooling out there. I mean, we've had DevOps for, what, 20 years or so? But you're seeing a lot of divergence simply because people are finding that exactly those difficulties in machine learning and deploying machine learning in production require a bit of a different mindset and different tooling, so you get the kind of multiple tools that do roughly the same thing. And of course, you know, the final point is probably there's a lot of not invented here mentality there. People want to do something in a slightly different way, even though there's not a huge difference in it. So that's sort of my take on why we have so much.
Yeah, that makes sense. Well, thank you so much, Ian. Are you going to be able to join us for the panel?
Likely not, sorry.
Oh, because it's actually right about to start. Anyways, thank you so much. Really a fun journey. Please make sure to join our Discord channel so that you can ask or answer the questions that some of the attendees may have, either now or later on when we upload the recordings. And yeah, thank you so much again. And I'm looking forward to reading more of your blogs about the new technologies that's going to emerge, and hopefully we're going to have the Kubernetes of the ML ops soon, where it's going to be pretty much a de facto standard, and everyone is going to converge, and you will have only one system to cover.
I doubt that, but we'll see.
Yeah. Yeah. Thank you.
Thank you.